So quiet, guys. No need to be so quiet. Oh, maybe there is a need. Are we good, Damien?
Yes.
Join us. So, hi everyone. Thank you so much for coming tonight. My name is Sasha and I work at RedHat. I'm in charge of our developer marketing efforts. I do a lot of things as part of that, but one of my favorite things that I do is actually organize these meetups and other vLLM events. This is our 40th, roughly, meetup in the last less than a year, almost a year actually, and it is our first one in Poland, so really excited to be here. Welcome. This idea for the Poland meetup actually started exactly 3 months ago at NeurIPS when Damien here approached me and he said, hey, we should do a meetup in Poland. And I said, that sounds awesome. And then a week later, of course, he called me on WhatsApp and he said, hey, how about that meetup? Let's do it. So I just want to give a shout out to Damien right here for organizing this and helping us with all of this. And Damien, by the way, is from JetBrains. Do you want to quickly introduce yourself?
So my name is Damien. I work at JetBrains AI, and we work on AI features in IDEs.
Awesome, and thank you for JetBrains for this amazing venue. I don't want to get anybody else in trouble, or I don't want to get myself in trouble, but I'm going to say that, I'm not going to say it's the best venue, but I will say it's top 5 at least. Maybe Michael, I know where you are.
Top 3.
You've been to a lot of meetups, and Nicolo, I know what you guys think about the venue, but we really appreciate the amazing venue, the food, the drinks that are about to come. There's drinks, Damien, right? Afterwards? I guess it's a surprise.
Stay for drinks.
So just a little bit about RedHat. So we love vLLM at RedHat. We're a leading commercial contributor to the project. About 25% of all the code that goes into vLLM comes from RedHat. We also build and maintain adjacent projects like the LLM compressor, LLMD, speculators, guide LLM. Actually, you'll hear about most of these, if not all, in the coming sessions. And one thing about RedHat AI, we're AI, open AI end-to-end, open being the keyword. Sorry, my mic was away. Open being the keyword, so open models, open inference, and then the flexibility of choice where you deploy that across GPUs and also CPUs. So, the community, I just want to say a few words to the community. vLLM is way bigger than any company. I know we're here representing JetBrains and RedHat, but it's much bigger than JetBrains and RedHat. Hundreds of organizations contribute to vLLM, and that's really what makes it so good. We're driving about 1 million weekly downloads of the project, 1.9 million actually last week, hoping that's not one-off, hoping that actually continues. But that's really thanks to all of you, so thank you for being and participating and using vLLM. I want to shout out our sponsors tonight for making this happen. So JetBrains, we already talked about. Thank you guys. NVIDIA as well. Thanks for organizing the workshop, bringing swag, and helping us with content. You guys are awesome. Both JetBrains and NVIDIA, as well as RedHat, as I mentioned, are active contributors to the project, and they'll share some of the awesome work they're doing in a few minutes. Just a quick audience warm-up. So get ready to raise your hands. How many people never used the vLLM? Never. Okay, so not 50%, but there. How many people are playing with vLLM? So you're using it, but not in production. Okay, almost the same. How many people are using vLLM in production? All right, so about 50% all the way. That's awesome. So we'll have a little bit for everybody. We'll actually probably a good time to go into the agenda. So we'll have a little bit for everybody, whether you use it, you play with it, or you use it fully on in production. So we'll start with an intro to vLLM and a project update from a vLLM maintainer, Michael Goin. I can't see Michael here. I hope that he's here. Where is he? Oh, he's all the way in the back. Thank goodness. So he'll kick us off and share some of the recent project updates. Then, Damien? Do you want to go to the rest of the
Yes, so the JetBrains panel, we're going to have a presentation on our AI features in JetBrains IDEs. And then we're going to finish with a demo of a feature called Next Edit Suggestion NES. So we're going to run this model on for example, on the DJX Spark, which you can see here. So it's going to be pretty fun.
That's awesome. Yeah, I saw Damien this morning spending a lot of time on the DJX Spark, so let's hope it's awesome.
It's a real demo.
Yeah, and after that we'll talk, NVIDIA will join us, we'll talk about CPU weight offloading in vLLM with FlexTensor. We'll do a coffee break. Note for speakers, please stay on time. Every minute you go over, it's less time that we have for coffee and drinks, so we don't want to do that. So please time yourself, stay on time. And then after the break, we'll have Nicolo, who is another maintainer on the project, join us to talk and introduce vLLM Omni, and then we'll conclude with how do you scale vLLM across Kubernetes with LLMD. Just a quick reminder before I pass it over is we'll have a survey at the end. It's super quick. 3 questions, should take less than a minute, but please, as you're going through these sessions, just think of what you want to say there. It would be really appreciated. We want to make this, as I said, this is our 40th or so event. We're going to be doing many more, so the more you can share with us, the better it will be for the community and for the event, of course. So, all right, I think that my time is up. Damien, you'll do another few minutes, and we'll pass it over to Michael.
Thank you, Sasha. And guys, thank you for coming here. Thank you for, to all the users, developers, maintainers of vLLM. When I started, using vLLM 2 years ago, I would never think that it's going to blow up this way. So vLLM is right now de facto platform, the go-to platform for academics to implement their ideas, for community to implement state-of-the-art, inference ideas. And it's also a battle-tested tool for, production. So it's pretty great. Today we have a great crowd in Warsaw. The vLLM meetups take place all around the world: Beijing, New York City, Paris. So I'm very happy to host you here. I represent JetBrains. Thank you for sponsoring and make it possible for me to have this meetup here. We have representatives of JetBrains here. So if you want to talk about JetBrains, there is Jarek right there. Please talk to him because we have opened an office of JetBrains Poland here a year ago. So we are pretty young, but we train all over the We also train a lot, but we hire all over the AI stack. So we hire for pre-training, post-training positions, for inference, for DevOps, LLM ops. So we're looking for a bright and skilled people. So yeah, join us, and I would say enjoy the meetup. And I hand it over to Michael.
Thanks, man. Hey, everyone. I'm really happy to be here in Poland. It's my first time. I've already had a great time here. My name is Michael Goen. I am a core maintainer on the vLLM project. I've been working on it for over 2 years now. And I'm a principal engineer at RedHat, where we have a very strong and growing inference optimization team. And yeah, I'll be giving you a quick introduction to vLLM, maybe a pretty light introduction, and then an overview on what we're doing in the project, especially over the last quarter, and how we've been pushing and where we hope to grow on the project soon. So let's get started. First we want to, of course, make sure you know what vLLM's goal is. We want to build the fastest and easiest to use and most popular open source LLM inference and serving engine. Pretty easy thing to achieve. We're already pretty much there. As you can see, from the quick start guide, we like to keep it really simple. To deploy, DeepSeek, it should hopefully just be like a pip install away. Or a Docker pull away if you're a Kubernetes freak. So what is vLLM? vLLM is a very popular project in the open source AI ecosystem. Apache 2.0 licensed, over 70,000 GitHub stars, over 800 PRs a week, and a similar amount of issues. Over 2,000 different contributors have landed code in the vLLM project itself. It's deployed on millions of hours of GPUs every week. We have a very active developer Slack, over 10,000 people. You're welcome to join. Slack.vlm.ai, best way to get our attention. Of those many contributors on the project, many of those come from very large companies, enterprises, academic institutions that want to drive forward the frontier of LLM inference. So as I mentioned, it's a very simple Python-based package. You pip install vLLM, you run vLLM serve DeepSeek, It's going to run it on your very expensive NVIDIA GPUs. And that's why it's so popular. It supports hundreds of different model architectures on launch. When the latest DeepSeek model comes out, when GPT-OSS comes out, when Kimi K2 comes out, it's supported on release because we've spent weeks ahead of time working with those labs to make sure that the model is well supported, and vLLM is the reference implementation. Of course, we run those models very performantly on NVIDIA GPUs, but vLLM, as a software library, offers flexible interfaces to support a wide variety of hardware accelerators and CPUs that want to plug in to that software interface. It, of course, runs models on more than one GPU and can have many different types of parallelism, which I'll briefly cover later, how to run the model on multiple hardware accelerators. And vLLM goes far beyond the inference engine itself. It's grown into a larger project where we have benchmarking tools and model compression tools, speculative model training tools, distributed inference libraries, which we'll go over a bit of those later today. And to sort of drive home a great achievement we had last year was nominated by GitHub as the top open source project by contributors, beating out like VS Code and Transformers and Codex, which definitely makes me feel better about the insanity of maintaining a project like this. As I mentioned, vLLM supports many different types of hardware accelerators through the software interface that it provides. And I really sort of want to drive home that vLLM's purpose is to fit into the ecosystem of all the models that get released in open source, all the accelerators that get released by hardware vendors and companies, and all the frameworks that want to build on top of these very expensive to run large language models. And it's sort of that middle ground abstraction, kind of like the Linux for AI, to abstract away the hardware and allow the applications or models to run freely and well utilize that hardware. So then all the end user applications can serve and just not need to worry about that abstraction. So that's like the base premise of vLLM, to efficiently serve whatever model you want. And now I'm going to talk about like what we care about today and where we're really pushing in the project. And sort of all 5 of these like main areas all correspond to channels or SIGs, special interest groups, that we have in the project, where we have weekly meetings sort of talking about and invite anyone to come and help influence how we build these key parts of vLLM. So first, let's start with the core. First we have, if you've been following along with vLLM, you're probably familiar with vLLM v0 and vLLM v1. This is sort of v1 is like a remake of the core of vLLM scheduler, model runner, and engine. And the reason why we built this was because vLLM v0 has been around for 2 years. It was sort of incrementally built, and we have many types of inference optimizations and systems built on top of that. And the cross product of the feature matrix had quite poor success between features. And so we wanted to deprecate this and build a new core transparently for the user. You don't really care about it. It just happens automatically, where we can support many more of these performant features, either system optimization features or model forward pass optimization features, and cross-product them with each other and have better success. So as we optimize or add a new feature to vLLM, hopefully it speeds up the very broad types of use cases and workloads that vLLM finds itself today with so many different types of users. Next, we have an investment we made early on as well, the hybrid KV cache manager. So as you've probably been noticing, the latest state-of-the-art models have increasingly had more than one type of attention. They've been trying to move away from global self-attention or full attention across all the tokens, rather preferring to use a lot of the layers with some type of sliding window attention or linear attention or state space models, so that attention doesn't keep growing exponentially in time and dominating as you go to longer and longer contexts, especially now with coding agents running for a long time. So vLLM's initial premise was introducing indirection or page detention block management of KV cache. But now we need to manage blocks of different sizes or with different restrictions with the different types of attention that we have, and the hybrid KV cache manager is meant to deal with that, particularly with latest models like GPT-OSS, Qwen 3 Next, now Qwen 3.5, and the latest Nematron models from NVIDIA. And this is really important to make sure that we keep that cross-product of feature support like prefix caching and KV cache transfer with disag PD, which we'll cover a bit later. Next, we have asynchronous scheduling, which is a really important feature for performance. This has been on by default for several releases now. We're on 0.17 now. But the key premise is as your CPU is preparing, both your scheduling and preparing the inputs for the current batch of requests you want to run on the GPU. We're doing that for the next request or the next batch, while the GPU is currently running the current batch, rather than running these in sequential, or rather one after the other. And so this allows us to, as the GPUs get faster and faster over time, which they certainly are with the latest Blackwell series, the CPU can sort of not end up as a bottleneck as much, especially as we have smaller models or rather more sparse MOEs, and have sort of greater operations that we need to do on the CPU as well. And we see very clear throughput improvements, especially as we increase the queries per second we're running on the GPU, and thus we're spending more time on the CPU preparing all those requests, taking them in and out of the running batch, or needing to do more CPU-bound processing. Yeah, this is on by default now. It works with spec decode, works with pipeline parallelism. So we're really happy we finally got this in. And what's next? vLLM v1 is already a very performant base. So of course, we want to rewrite it. We're working on Model Runner v2 now. Although the purpose of this is, we have pretty good performance with vLLM v1. We've achieved a lot of features in there. However, if you look at the GPU Model Runner in vLLM v1, it's I think 6,000 lines of code or 7,000 lines of code. Not too bad for Python, but it's pretty hard to work on, and we don't really want to add more features to keep growing that. So Model Runner v2 is really a step back and saying we want to make this more modular. We also made some I think errors in the design, and we're working on that now, and that's going to be several months of work down the line, but ultimately should allow for us to accept many more types of features or modifications to vLLM that we would previously be more cautious about without seeing the benefits of it, just because of the growing complexity of a sort of monolithic design like v1. And some of the things that help justify this is we want to decouple persistent batch. This was a decision we made in v1 to introduce a persistent batch where as we're scheduling requests, they need to be kept in contiguous block tables on the GPU. And so we have this contiguous, or rather persistent batch that as we add a new request, maybe it's a prefill request or it's a decode request, we need to shuffle the different requests around in this persistent batch, and depending on what device we're on. And this is really slow, this is really complicated. So in v2, we want to completely separate the state of what requests are using what blocks and what's the actual input to the GPU, which the latter needs to be contiguous, the former does not. And we'll just construct this input block table on each forward pass, which is now much easier and not a bottleneck now that we have asynchronous scheduling as a first-class citizen, which is the key second point, which is we absolutely need async scheduling. The CPU should never be affecting the performance on the GPU. So CPU operations must be non-blocking, which we achieved in v1. However, this introduces some race conditions because we have dependencies, obviously, between the CPU and the GPU. In v1, we achieved this with a barrier that tells us whenever the CPU is done with everything it needs to prepare and the GPU can now take the shared state. However, this is like really complicated as you add more features, more buffers, you need more things to be synced between the CPU and GPU, and so it's really error prone as new features get developed in vLLM. In Model Runner v2, we eliminate this race condition entirely by just separating the tensors and making a temporary state, and that temporary state is what gets explicitly copied to the GPU. So it sounds really simple, but from a code perspective, it makes it very explicit of what is going to end up on the GPU. Unless you didn't copy it to this state, then it's not going to happen. This also allows us to make use of other more modern GPU features, like on Grace Blackwell, universal memory addressing, but I don't have enough time to cover that here today. So let's go ahead and go on model performance or speed of light. First, in talking about performance, we need to talk about accuracy. You can't really separate these things. It's not really valuable to make something fast if you don't keep it accurate. And vLLM is really important in the community as a reference implementation for so many models and libraries and research results. So, we very, very much care about vLLM maintaining its accuracy and even pushing, features used by researchers like batch invariance to, make inference as deterministic as possible whenever people need it. Even fighting very minute log prop differences. Yeah. So, we also prioritize performance, of course, not just in our benchmarking and tuning, but also as a consistent thing that we run within our CI. We spend, $100K plus a month on CI to test and benchmark vLLM across a wide variety of hardware in order to make sure we aren't regressing performance as we go from, week to week or release to release. And part of this has resulted in, moving our releases in CI towards a 2-week release cadence, so the people that are relying on the latest performance features in vLLM can more, readily rely on features coming out on stable releases on a regular cadence, and they're not stuck using the nightly so much when models release on day 0. As for what we're doing specifically to improve performance, we're very clearly doing this with public benchmarks like semi-analysis, Inference Max. Here, this is actually from a blog we published with NVIDIA on just between 1 month, improving the performance on GPT-OSS on B200 GPUs across the Pareto frontier of, at low latency and at high throughput. Doing this through new kernels that we integrated from TRT-LLM generation or Cutlass backends. Optimizing existing kernels, doing graph fusions, fusing multiple operations together using Torch compile, or writing custom kernels to substitute those in. Of course, we want to improve the performance on specific benchmarks or model workloads, but we also want to make sure that the default performance is increasing for users. As you can see from this bar chart, each one of these things on the x-axis is a different flag you could activate on DeepSeek R1 on a B200 to get better performance. And if there's like 60% faster performance hiding behind a bunch of environment variables or CLI arguments, we don't want you to have to do that. On the right, I have a benchmark of running DeepSeek R1 on TP4 on B200 between vLLM 0.14.1 and 0.17. And it's a very simple vLLM serve command, and it's 50% to 100% faster at low latency and high throughput just between a couple releases, which is exactly what we want to see. And your hardware is just getting better and better over time thanks to our software, which is hopefully the purpose of software. Next, we can also improve things by adding new methods and aiding researchers, like the recent Eagle 3 speculative decoding method. This, is a way to train a very lightweight extra layer or a couple layers to your model that predicts multiple tokens in parallel, which you then verify through your original draft model to hopefully predict multiple tokens per forward pass rather than one output token at a time. This has been integrated in vLLM for a while, and we've been pushing the performance on Eagle 3, on MTP, and other methods that have been widely adopted. And as I mentioned, we're working directly with researchers, from AMD, from AWS, from other labs, that are introducing more modern parallel drafting models like PARD or Parallel Eagle, where we're decreasing the cost of drafting, with like these new Eagle methods or draft models, and improving essentially the output throughput you can get per user, even at very, very small, low latency or low batch workloads, as this is increasingly important from your agents as you want to get, hopefully not 50 tokens a second from your coding agent, but maybe 200 or 300 tokens a second. So really excited to be like aiding in this research, and this goes directly, not only in vLLM from the inference side, allowing these new methods to run, but also most importantly the training side, so that when you have your own model that you fine tune, or a new model in open source that didn't come with a speculator, we've built the library speculators under the vLLM project. We released a blog on the 0.3 release. So that you can train your own speculators, Eagle 3 methods or Parallel Eagle that we're integrating now, using vLLM as the inference engine to generate your training data, training your speculator to be accurate for your data set, for your workload, and ultimately deploying that in vLLM together. If you're interested in that performance, take a look at speculators and training your own speculators. You can get really great results if you're willing to dedicate the time. Next, I'm going to talk about distributed inference, which is a really big thing for vLLM. As I mentioned, there's many different types of parallelism. We started pretty simply with tensor parallelism, pipeline parallelism back in the day, but now with large MOEs, we have expert parallelism, data parallelism with different types of attention, and finally disaggregating prefill and decode, which is what I'll talk about here. What this means is, if you don't know, P, or the prefill here, is the work you're doing for processing your input tokens or context. D, or decode here, is what you're doing when you're generating tokens from the model. And generally, you can only generate one or a couple tokens at a time per forward pass. And fundamentally, we want to talk about these as separate operations for the LLM to do, because prefill is an inherently compute-bound operation. We're using all the tensor cores because we have a large batch size of tokens to process. Whereas decode, we have maybe a couple tokens, a few dozen of tokens. We can't really saturate the tensor cores on your GPU, and we're more inherently memory bound. And also, as a user, you are probably most looking at your time to first token. When do I first get my response from the model? And how quickly is that response continuing to come out? And those are the prefill versus decode operations that you're seeing. And if you're doing one deployment of vLLM that's serving both of these very different operations, you can get very sort of wild latency differences on the tokens coming out of the model if suddenly that node needs to do a big prefill and your decode batch takes more time. So we want to separate and decouple how prefill performance and decode performance is scaling, especially as these models get larger and larger, and particularly for MOEs, where it's a variable amount of memory that we're accessing for each batch. So that's just a fancy way to say that we are disaggregating these workloads that vLLM finds itself in to better meet whatever latency you need to hit for your use case, and we need to transfer the KV cache between these multiple nodes that are essentially doing the job of one vLLM instance before. And we achieve this through, again, a flexible general interface that people can plug in called the KV connector. Here we're using this as for the Nixel connector, which is a library from NVIDIA to transfer between devices. But we also can integrate with LM Cache, with Mooncake, with whatever KV connector you want to develop to offload your KV cache to storage, to CPU memory, to whatever sort of device or method you want. And this has been already used for a lot of other things. But really where we're using it so intensely is to scale this KV cache transfer for disag PD. And the importance of disaggregating your prefill and decode is really important. We have this metrics chart shared by Mistral in a previous presentation of their 99 percentile intertoken latency in an aggregated standard deployment versus a disaggregated deployment, and they're able to get an order of magnitude better latency here and on the same number of GPUs by moving to a disaggregated deployment and scaling their prefill and decode work separately. Next for parallelism. I mentioned scale. These large MOEs like DeepSeek that are hundreds of billions of parameters, while they can maybe fit on a single H200 or B200 node, to get the greatest efficiency or price per token out of them, you sometimes want to deploy them on multiple nodes of devices. So here we have a deployment of one MOE running across 32 GPUs across 4 nodes. And things like tensor parallelism don't work so well here, especially when the experts on these models are so small. So we can apply expert parallelism across the MOE, splitting up the maybe 128 or 256 experts we have into sections of maybe just like 4 or 8 on each GPU, and then doing data parallel attention across all those GPUs, and really handling very large decode-heavy workloads. And serving hundreds thousands or tens of thousands of requests concurrently for very sparse MOEs on these large multi-node deployments. And this is the key thing that DeepSeek and Anthropic and other like large frontier labs are deploying their large MOEs at scale at, and with vLLM and LLMD actually. We show we're able to deploy, a DeepSeek R1 across dozens. I think here we scale up to 96 H200s, getting 2,000 tokens per second. Those are output tokens per second per GPU. Running one model across 96 H200s. And there's a lot of work that goes into this. We have blogs and stuff all about that. But it's great proof of showing that you can scale up to very large multi-node deployments. And then of course H200s are a little bit out of date now, and we show you can apply the same optimizations on the latest and greatest like GB200s or Blackwell series. Here we're show on decode throughput moving from 2,000 tokens per second to 10,000 tokens per second per GPU. So getting 5 times the amount of performance for the same GPU, which definitely doesn't cost 5 times more per GPU. And again, working very closely with NVIDIA on getting the best performance out of the latest hardware and juicing the value out of the faster hardware and interconnects and so on. So next we have multimodal, which is obviously a really important part of vLLM. Many models are multimodal these days. We already mentioned prefill decode disaggregation. We've also worked on encoder disaggregation for the vision or audio encoder part of your large language model. And so disaggregating that, also very compute bound intensive preprocessing of your multimodal data and transferring that to your actual like autoregressive backbone of the model once it's been encoded. And again, we have a blog showing the benefits of this at different scales of deploying vision language models. Pretty recently, we introduced Streaming real-time inputs to open source with the launch of Voxtral real-time and Quen ASR. So this is something that previously was only really available in closed source APIs like OpenAI or like Grok. But with these like initial like open source models that are really useful for like text to or like speech to text in a streaming real time fashion, we introduced changes directly into the scheduler, the core of vLLM, to allow for new inputs that come in for existing requests as we're generating outputs for them. So of course, run the models, build new use cases on top of them in open source, but also go read about the scheduler changes and what it takes to achieve this in an open source framework like vLLM. Lastly, we have vLLM Omni, which is looking forward to the future of not just multimodal input in large language models, but also multimodal output, supporting diffusion models, and ultimately mixtures of different types of transformers or other ML models where we're plugging together diffusion transformers, autoregressive backbounds, and so on, which Nicolo will cover in detail for you later today. And finally, RL. This is a really, really big use case of vLLM now, as this is the place of training that we're scaling in right now. But it's really important to realize that reinforcement learning, even though it's a type of training, is actually dominated by inference. It's 80 to 90% of the time is spent in inference, because in order to get your agent working in all of these environments, you need to do a ton of inference, a ton of parallel requests, and letting that agent run for tens of thousands of tokens to explore your environment, to judge how it goes. And then you're doing one forward-backwards pass through the trainer to update your weights. Then you need to update your vLLM weights, and then run all the inference again. And so vLLM has been a really key part of the RL scale-up that we found ourselves in the AI community today. And as a result, we've worked to build native support into vLLM for RL, and it's been adopted by many of the leading RL libraries in open source, and it's been great, learning from them on how vLLM needs to grow. Again, as a user of vLLM of these, now tool calling or agentic models, we have to support the APIs that people are using, like the Responses API from OpenAI, on like the GPT-OSS launch to work with various coding agent libraries. The V1 Messages API from the Anthropic API, so you can use vLLM natively with like Claude Code or other coding agents that use the Anthropic API. And again, like vLLM as a rollout engine for reinforcement learning, we're pushing on greater utilities and performance for making the weight syncs or asynchronous reinforcement learning as easy to do as possible. Online quantization, so you can run your rollout faster, or run your model on less GPUs and scale out your RL to a larger scale, and even memory efficient RL, so you can train these models on smaller groups of GPUs for local inference or local training. So to recap, we have lots of things we're working on in vLLM. These are just some of them that I want to cover that we're focusing on today. And happy to talk later or introduce you to some people if you're interested in some of these topics. And as I mentioned, sort of all of these groups are related to some sort of channel or special interest group we have in the vLLM Slack, and they're listed all on our roadmap. So please check out these links if you're interested in getting involved or joining the meetings and catching up with what we're actually doing on a day-to-day basis. So yeah, thanks a lot, and I'll hand it off to JetBrains team.
Thanks. So I will be starting with the JetBrains side. Yeah, so it will be hopefully rather quick. So we do a lot of stuff in JetBrains, and for some stuff we need some custom models. And historically speaking, a lot of things they started with like different code completion initiatives. For instance, sometime pretty long ago, we only had completion in this lookup or pop-up window, and even in there, we used a lot of machine learning to do the ranking of individual suggestions. Because if it's like tens of or like even hundreds of suggestions, you have to rank them somehow. Then we were kind of limited a little bit by this experience, because you cannot really fit longer suggestions in such like places. So we added the inline version as well, that kind of allows us to make suggestions where lookup is not available, or it does not really fit the suggestion we want to display. For instance, it might be like multi-line or something like that. For this, we initially started with very custom, very small model, it's only 100 million parameters. It's not even like, by today's standards, it's not even a model, right? So we initially did it it was specialized in every language. It was a separate model, and it worked pretty fast. The latency constraint that we had were very tight. It had to run on commodity hardware, so anything that can run in IDE should be able to run this with minimal resource overhead. And we used initially Llama CPP for it. Then we moved to the cloud, and I think we started using vLLM pretty early for it. So we had we had to scale the model, and we also had a bunch of constraints in what could be the source of data for this model, not to break any sort of licenses and address all of the privacy and security concerns. So for this, we built from scratch Melon and open source it, so you can download it and use it for your language of choice. It is also a very small model, but it is trained specifically with one task in mind, and this kind of allows us to make it punch a lot higher than its weight. Yeah, so there will be more models that we will release in this model family. If you have never done this code completion models, you might not know, but they do not see the file the way we do it. So you have to chunk the file in several pieces, so prefix and suffix, and then kind of combine them in the reversed order so that the model will be able to understand what this all is. And then we force the model to generate some text that will be inserted between the two pieces. It is pretty straightforward, but at the same time, it kind of limits the model. But we will touch on that a bit later. So adding additional context or improving the model or the data is not the only way to make the product better. And we have a bunch of other tools. For instance, we can add smaller models throughout the pipeline before we call the main generation model or after we do it, to kind of that is trained on user signal directly. With this, we can move much faster in the improvement rates. We can eliminate some of the requests that will never reach the model or will never be accepted by users. Similarly to how pop-up completion it limited our ability to give the model more options and to do more. We had the same with the typical inline compression prompt. So it only allows you to do modifications in the immediate position of your caret, and it can only generate more stuff, right? So this is helpful if you are writing new code, but if you are changing the existing code, it's not as helpful. And for this, we need to expand the action space a little bit and add an ability to delete and thus modify arbitrarily the code. So we call this next suggestions, and we will be demoing this a bit further with the custom model. So all of these capabilities, they kind of blend in together to support existing user experience, but also to add something on top. JetBrains has access to understanding of the code that not many other vendors have, and this kind of allows us to build on this foundation. For instance, when you are editing the code or you are renaming a symbol, right? Your project might be very large, so no single LM will realistically kind of will be able to chew through it all. But by building the harness around the model, we can help it to capture the kind of ripple effect that your edits are doing on the code base, and provides kind of deterministic and fully reliable workflows that you expect from JetBrains tools to perform the refactorings in a very stable fashion. So for this to happen, we had to take a step back and think about how do we express your intent to the model, and how do we get the intent from the model back so that we can make a suggestion for you. We had to add temporal and semantic context to the prompt somehow. And in your spare time, you can think about how do we do this to make it all KV friendly. Yeah, so talking about the future, there are several things going out in the industry. I'm not sure if you've noticed, but basically agents, they kind of change the way we work with code, and this influence will likely stay, or it will likely change even more. So we see this as like another mode of communication. Essentially, with chat, this is like a synchronous mode where you have to put your thoughts in the chat and then let the agent execute them. With flows in editor, the agent is it's also there, but it's kind of ambient, meaning that it picks up on your changes that you do naturally through the editor, and then it can help you with the suggestions. Yeah, given we view this as an editor, there is a very kind of cool initiative called Agent Client Protocol, which kind of allows us to expand our tools in other ecosystems and to welcome other tools in our ecosystem to make it truly like open and integrated. Yeah, that's kind of it with my part. I had to shorten a few things. So if you would like to discuss these things further, please meet me somewhere, or anyone from JetBrains for this matter. Yeah.
Yeah, looks like we are slightly running out of time, so I probably need to hurry. So, my team is responsible for processing requests from thousands of users in our IDEs, both in cloud and local on devices. So our main core feature of our IDEs is code completion and code next stage suggestion. We power it by our services, but we also have different features like natural language completion, grammar error correction, and also embeddings for semantic search. But today I will mostly focus on code completion and code modifications. So the main challenge in this domain is latency, because if you type some code, you would like to feel the response of the LLM immediate. So our models and services usually has less than half a second to generate some response. And that's why it's pretty important to minimize any chance of queuing. And also our inputs are significantly bigger than output, so 3K to usually tens of tokens output. So initially in the development of AI in JetBrains, we faced an early decision to rely on different external providers or run our services on our own clouds. So we choose to run our own inference services because of several reasons. First, we wanted to control our expenses and to be sure about the data privacy. Also, our models are pretty small, so our cloud models are usually 4B and 8B, which is slightly out of the focus of big inference providers. And some of our pipelines are not just calling LLMs, they use different models with specific architectures, different customized pre and post-processing, and also multi-model pipelines for specific features. What is our setup? Initially, we started from DeepSpeed. It was more than a couple of years ago. It was good to have some proof of concept, but there were some issues with DeepSeek. For example, it has no continuous batching. Also, they had some specific issues with memory, so we needed to implement such a semaphore to control the flow, and it was totally killing all performance. So 2 years ago, we migrated to vLLM version 0.2.3. I think we were one of pretty early adopters of this engine. And in production, and it was pretty nice to have it because it gave us a straightforward way to conduct different experiments with multiple configurations. It was pretty flexible for our pipelines. And there were 3 big important features for us. First of all, continuous batching, which improved our throughput for 6 times in the beginning. Also, we got output log props, which were pretty important. I will say why. And we also had an ability to use custom per request logit processors. So let's continue. Why do we need log props? First of all, our pipeline is not just calling vLLM and sending the response. It also contains some pre-processing and post-processing. We have several filter models in the end of the pipeline, which usually evaluate the confidence of the big model and evaluate the flow of the user, deciding what to show or not to show. That's why log props were just crucial for us. Also, we needed custom log props, logit processors, because we wanted to implement a token killing feature. I will briefly describe it right now. So, users usually type their code in characters. LLMs processes some input in tokens. So there is always a chance that some user will stop in the middle of some token, for example, like this one. And the LLM may generate some token which is not expected by the user because this token is maybe slightly more important for her. So our idea was to crop a part of the prefix, for example, like this, based on some certain strategy, and then force the LLM to complete this part of the code. Right now, we, of course, can use some ready-made solutions like structured outputs, but a year ago, there was nothing like that, so we needed to implement it by our own forces. So we will generate more tokens, but it would be better for the exact part of the code. So when you have a service, you need to deploy it somehow and observe its metrics. So we use some default stack with Prometheus and Grafana for easy visualizations, different notifications in Slack and Sentry, and Loki for deeper analysis of errors. Also, for latency-sensitive cloud solutions, it's pretty important to place the server close to the user. So we decided to run our services in 3 different regions of the world, pretty close to the main places with software developers. And since our model is pretty small, we deploy it using 1 service per GPU approach, and it allows us to easily scale it on demand because when the load grows. So when we deployed the service, we started to collect low-hanging fruits. The first one was prefix caching. So it was pretty easy to implement our own sticky sessions based on some experience, and we easily get around 25% of throughput doing just nothing, I would say. So right now there are some also ready-made solutions like Dynama and LLMD and production stack from vLLM, but that time we implemented just our sticky sessions and it worked pretty fine. So the second low-hanging fruit was quantization. We started from FP16, then switched to dynamic FP8, then quantized it into static FP8 and get extra 35% of throughput by just converting the model, which is also pretty good. So after that, we switched to later and maybe more complex optimizations. We tried speculative decoding and tried both n-gram approach and draft models. we compare the results, and for our use case, n-grams were much better because they're latency free, I would say, because it's pretty cheap to like create an n-grams and match them. But later, we luckily found the great solution, suffix tree, created from on prompt. It's pretty close to n-grams, but much more effective. So we get 75% of acceptance rate of this speculator. So thank you, Snowflake company, because you created this solution and open sourced it. It was pretty nice from your side. So just taking some pretty mandatory optimizations and taking correct parameters for vLLM, we got, I think, around 4 times better throughput in 2 years, and it was pretty easy to get and pretty easy to implement, I would say. So our current state is hundreds of thousands of users per month, sending us hundreds of millions requests per day. We have many services, like 14 exactly, running off 6 different types of GPUs, and we have some plans for future. First plan is to try and adopt TensorRT-LLM because there is no one-size-fits-all solution, and it's nice to find the exact solution for every case. Right now, we adopted already vLLM for most of our services. We also run something on Onyx runtime, on bare transformers, and we tried slightly TensorRT-LLM. And the second big thing is disaggregated prefill, because I would say that for now, it doesn't make sense to run some disaggregated prefill for 4B or 8B or even 10B models, but we are making some step towards the agentic models. So in this case, it definitely makes sense to try and run it. So it was nice to see you here. Damian, please.
We are not done with JetBrains part. Can you hear me? Yes. Okay, perfect. Okay, so demo time. Let me just quickly take a look what we have here. Cool. Misha and Oleg already presented and explained how the NES feature works in our IDEs. So by default, how you use this feature is basically you have your IDE set up on your machine, and it talks to a model which is run in an inference engine in the cloud. But we also want to enable our users to use your own locally hosted endpoint. So the NES model, those types of models are not usually too big, about 10 billion parameters. So you can make it run fast locally. Why would you like to run this locally? One reason could be costs, right? When you use APIs, your costs scale with tokens. When you run them locally, you just pay upfront for your hardware, and then the tokens are for free. And the second, I would say, reason is, for tinkering. You get to play with the model, you get to fine-tune it, apply different optimizations. So it's like a pretty cool thing for hackers and tinkerers. So this is what this demo will be about. So what I will do is here I have my MacBook. Here, there is the DGX Spark AI workstation from NVIDIA. Not everybody can see, but it's here. It's connected to my MacBook. So basically, what I'm going to do is I'm going to deploy the NES model locally on my MacBook in vLLM, and it's going to be a disaster. It's going to be really slow. And then I will apply a set of optimizations to the model. Some of them you already, those of you who are at the workshop, you should be familiar with those optimizations. And then this optimized model will be deployed locally on this machine. And we're going to see a massive improvement when it comes to UI. Spoiler alert, the optimized model on the GX will be almost as quick as the cloud deployment. So it's going to be a pretty massive increase, right? So this is what we do by default. This is what I'm going to do right now, so deploy on MacBook. And then finally, we're going to deploy on DGX Spark. So the model. I'm going to use, for the purpose of this demo, the open source model from the company called Z. So they released this model around a year ago. It is a Qwen 2.5 coder, which has been fine-tuned for this task of next edit suggestion. So you can see the example of the prompt above. So the first one is the instruction, kind of like a system prompt. So you tell the model what it's supposed to do. The second one is the history of user edits. So basically the suggestions, they require, let's say, your past edits to be able to infer your current intent. And then you have the part which you want to, like your current code which you are working with. Notice the three tags. The first one is editable region start. The second one is user cursor is here, and then editable region end. So between those editable region tags, you have the part of the code which the model is supposed to potentially modify. And we also tell the model where our caret, where our cursor is, so it also can infer, like where we are right now, what we want to do. And then the response, so this is the part which basically triggers the generation. So the model rewrites essentially the editable region for us. Okay, so first local deployment on MacBook Pro. I will first just run it just to save a bit of time. So I have here the on my MacBook the MacBook installation of vLLM. I'll just run it right here. So on this side, you can see my terminal. On this side, I have PyCharm, so our IDE. This is still like an experimental, let's say, not even nightly, like a build version, internal version for this demo. So what I'm going to do is I will just connect this IDE to the endpoint, which we're going to be using. And just for the sake of simplicity, I'll just copy it over here. So I need to go to my registry and just change this. Okay, port 8000. Okay, startup complete. So yes, so regarding the installation of vLLM on MacBook, well, it will not be fast. So vLLM does support MacBook, I mean Apple Silicon as a deployment target, but only CPU. And plus, it's lacking a lot of cool features, so you will not be able to run speculative decoding. You're going to get some assertion error. You will not be able to run dynamic quantization to FP8 because the vLLM at this point supports only, for MacBook Silicon, it only supports FP32 and BF16 as a data, like the precision. But anyway, we can run this, and actually we just run the server, and now you can see that I can change something in my code, for example this, and then the vLLM server should basically notify us that it received a request, but it will take a lot of time to process, essentially. Yes, right? So you can see the vLLM got the request, and right now it's processing it, but notice the very poor throughput. So we're going to essentially get a response from the server in like 30 seconds, which is absolutely not the user experience you want to have, right? So let me just, let me just close it for now. And this is a failed experiment. So what we can do instead? Instead, we can use DJX-Spark. Why it's relevant for our local deployment? Well, first, it runs on NVIDIA Grace Blackwell architecture, which makes FP4 like a native data structure, like native precision. So we can basically quantize both weights and activations down to FP4, and we can run compute in FP4. So it just means that you can basically take a very big model and you can compress it down very heavily, and this model will be like natively run in very low precision on this hardware. It has also a lot of unified memory, so basically memory which most of it, a part of it, can be both accessed by GPU and CPU. So you can really load very beefy models into DJX-Spark for either inference or for fine-tuning. And finally, it's an NVIDIA product, so if you have tools which run on NVIDIA stack, like vLLM, it's going to be supported out of the box. So what we can do is we can take this this model, and we can run this on DGX Spark, let's say without any compression, so in BF16, and we're going to get some kind of performance. But then what we can do is we can take one of the tools from the vLLM ecosystem, which is LLM compressor, and we can compress the model, so we can apply, let's say, the first step. So we're going to only quantize weights down to 4 bits, and this should already help us because we essentially need to spend 4 times less work when it comes to fetching weights to do any type of matmos. So this is the first improvement. Then what we can do, we can also quantize the activations down to 4 bits, which should in theory help us even more because right now the compute will be done in 4 bits, so we can have potentially very large prompts, so the prefill will be faster. And then we can apply additional, let's say, deployment level optimizations, so speculative decoding, for instance. And notice that for our problem, speculative decoding will be very useful because what you do essentially, as I showed you before, you feed most of the stuff which you will have in your output, so the rewritten code is already in your prompt, right? So it's very easy to speculate those tokens because the model already sees them in advance. So speculative decoding for this problem is extremely useful. Also, one thing which I'm totally not mentioning here is that quantization is not a free lunch, and it may cause some degradation. So always, even for the purpose of this demo, I completely I'm ignoring the fact that quantization may basically just harm my correctness of my results. Yes, regarding LLM compressor, I just wanted to say that all the code which I use for compression is taken almost verbatim from the examples in LLM compressor. So you can just go there, take a look at the code, and do it yourself. By default, we're only quantizing the linear layers, with the exception of LM head. Why? Because LM head is extremely sensitive to the precision, because those embedding outputs, they basically decide which token will be generated next. So they have to be handled with care, caution, and precision. All right, the next part is benchmarking. So once again, we used a tool from the vLLM toolbox, which is GuideLLM. GuideLLM is basically a tool for benchmarking, which we like a lot because it focuses on different SLOs. So SLOs are basically things which you, like your target goals, which you care about during the inference. So what I care about here is not throughput, it's latency. I'm basically a user of my IDE. I have my machine here. This machine only serves me. So I'm gonna send very few requests, maybe like 1 request per second, 2 requests per second. And I only care about receiving the response as fast as possible. So my UX, like the usage of my IDE is as snappy and smooth as possible. So I care here about latency in this case. So what I can do is I can fire up GuideLLM, I can fire up my model, different incarnations thereof, and I can benchmark it. So GuideLLM basically gives you like a nice CLI. You specify the target, which is your endpoint. You specify the profile. So I'm gonna basically bombard my my server with constant requests. Data. I actually give 2,000 examples from our actual data set, which is like it mimics our real user traffic. So we have, for example, like prompts up to 5,000 tokens, and we have roughly 500 output tokens. And then I basically run several experiments. So first I send 200 requests at the rate of 0.25 RPS, and I increase this up to 1.5. I use 10% of requests for warm-up, and I generate 256 tokens. So it very much mimics, let's say, our real use case. Good. And now the results. So basically, what you see here is on the x-axis, requests per second. So the further you go, the more requests, the more frequent the requests are. On the y-axis, you have end-to-end latency. So notice that for the baseline, so for the yellow line, to get a response from the vLLM server, we need almost 20 seconds. So better than 30 seconds in case of a MacBook Pro, but still something which is just rubbish when it comes to UX. And then when we do the weights-only quantization, you can see that this latency goes down because we need to basically we can quickly fetch the data from memory. Then when we quantize also activations, we are also a bit better. Perhaps we can process, we can run prefill faster, I suppose. And then when we put optimizations on top of that, we absolutely go into a very good range when it comes to end-to-end latency. So you basically start with around 20 seconds initially, and we go down to 1 second, which is really nice. Those optimizations, which I mentioned here, is prefix caching and speculative decoding. I think I used engrams here for this benchmark. Yes, I'm gonna start actually. So what I have here is I'm logged in to my DJX Spark. I already have the container built for running here in the NVIDIA ecosystem. So what I'm going to do is I'm going to run this this model, the 4-bit, so weights quantized down to 4-bit, but also activations quantized to 4-bit, and I will also use the suffix decoding as my speculative decoding method. So let's run this. It's going to take some time to basically initialize. In the meantime, I can also show you the Docker file. Pretty simple. We just pull a vLLM NVIDIA base image. We install Arctic Inference, which is the library which allows us to use this fancy, very useful speculative decoding method. We built Arctic Inference for this particular architecture, which is Grace Blackwell, and then and that's basically it. So right now, I'm still waiting for the model to initialize. At the same time, I can already use the proper endpoint for my local inference. By the way, what you see here is like what I'm doing here, like swapping the endpoint addresses. This is not how the final experience for the user is going to look like. This is still, like a demo. So for you, the UI will be much simpler. We won't have to go through registry and whatnot. Okay, this looks good. Let the model load, right? So to reiterate, right now I'm running the most optimized model on DGX locally. So we are not talking to any API in the cloud. And as soon as it loads, give it some more time, we're going to be able to basically run this, basically use the Nest feature in our IDE using the local deployment of the model. We're almost there. Oh gosh, if I knew, I would start this command earlier. Yeah, if there are any questions, I'm very willing to answer, just to kill time. but the time is over. Okay, of course, yeah, you have to. It's called GB10, so it's basically a so it's a Gracewell-Blackwell architecture. Yes, it's completely different caliber from the data center GPUs, right? Like H100s, B200s. Yeah, but it's pretty useful for, I would say, prototyping for your like consumer use cases. Okay, so we have the server up and running, and let's just play with in the IDE. So I can just, I don't know, sampling NVIDIA, sampling, I don't know, something group. Just to have the just to make it visible. See, so you can see that it asks me to press tab to complete, and this is all very, very snappy, I would say. Right here, now, tab, tab. Don't look at the quality of those suggestions. I told you, it's a very, very quickly quantized model. It will not have the best, suggestions. But the point is, it's very snappy, and you can use it as if you were just using the cloud deployment, which uses much more sophisticated hardware under the hood. Yes. So this feature is not yet available, but will be available maybe in the next release, or maybe the release afterwards. But the point was to show you that you can basically, you don't have to rely on APIs. If you are a tech-savvy person and you like to tinker, you can just do stuff on your own and hack things very, very nicely. Yes, this concludes the demo. Thank you very much. And NVIDIA, speaking of which, Błażej. Do you want this or I know you probably you have to use the microphone. Okay. Yeah, okay. Those.
Hello? Hello everyone, my name is Błażej Kupiak. I work as an engineer for NVIDIA, currently on the FlexTensor project, and this is PyTorch base library prepared for efficient prefetching and offloading of weights during inference. So if you have the model that do not fit into single GPU or do not fit into a single node, it might be the case for you to use this library. Also, it may help to save the memory for KV cache or reduce the communication overhead between nodes. So if you can fit the model into a single node, you don't need to have this kind of stuff. Assumption and goals for this project was to have zero or close to zero latency penalty while prefetching. Everything should be automatically profiled upfront by library, and it should be kind of native Torch API library, so it can be integrated with any framework, also with vLLM, of course. As I said, it will be automatic profiling at the beginning of the inference, so it consists of a few steps. First one is like discover of the layers that should be offloaded. So as I show you later in the API, how user can indicate which layers should be offloaded. In the first step, we discover which tensor should be offloaded. Then we measure execution times of the layers and transfer times of the tensors. And then, based on this information, we can create optimized profile. I will show it in in a few pictures to show the concept, how it works. So we load the model into CPU memory, as it may not fit into a single GPU. Then we discover which layers will be offloaded. In this case, let's assume that that layer 2 will not be offloaded, the rest will be offloaded. Then we iterate over layers, and for each layer we compute time. We copy it to GPU memory, check compute time, check tensor transfer, and gather the statistics in some dictionary. After processing all the layers, we have all the information that is required to build the profile. And the profile consists of like two parts, maybe not two steps, but two parts. First one is like the decision which tensor should be offloaded. So let's assume that optimization strategy decided that tensor T11 in the first layer won't be offloaded, so it will be residing in the GPU memory all the time. And for the fourth layer, there will be two tensors that will be residing in the memory, and for the fifth layer there will be one tensor. So the rest of the tensors will be offloaded and prefetched during the inference. And second part of the optimization is to we call it the GPU memory block assignment. So we assign for each layer, we have the set of memory blocks in GPU pre-allocated up front. I show it, I describe it, I mean, I drew it here just 2 blocks, but usually we use like 4 or 5 blocks for huge models. Just for clarity, it's 2. And during optimization, we choose which layer should use which block. And during the inference, it works like this. So when the layer 1 is loaded into block 1, we are transferring layer 3 to block 2. And when the execution on the inference is on layer 3, the transfer of layer 4 is to block 1. And so on. Yeah, so like summing the idea of the profile creation, we use layer compute times and tensor transfer times, and use some strategies some strategies for creating the profile. So we have a few implementations, some greedy, differential involution based, and global optimization. We try to merge some techniques. I won't go into details in this step. And after optimization, we have the set of tensors that are chosen for offload, and block assignment, and the schedule of prefetching of weights. So during the inference, there is no profiling overhead because it is done up front. The execution is deterministic, and we should have minimal GPU footprint if our profile is created in optimal way. Okay, let's go to the API. We try to make it quite simple, so you can load the model as usual, then create the simple config. I think the most interesting part is the module pattern, when you choose which layers you want to offload. It also supports the wildcards, so as usual in the huge models, there is some module list of a lot of layers, so you can just pass the layer .star, and all the layers will be offloaded in this module list. You can add also other layers that you want to offload. When you when you call the offload function with passing the model and config, and you get the patched model, that can be used in inference and doing the offload behind the scene. According to vLLM integration, we had to write the model loader that will load the model on CPU and make some initial weight preprocessing, and the worker that uses the model loader for model loading and runs the warm-up and profiling and switches to inference and applying the profile that was created. This is example how it can be run. So FT enables indicates that we want to use offload, and usually you use the parameter FT max GPU mem fraction, which indicates that what fraction of the memory can be used by weights. So in this case, 0.7 of the memory can be used by weights, and rest should be offloaded. Possibly paying paying for the penalty for the higher latency. Yeah, the TP and PP is supported. Data parallelism and expert parallelism is in progress. Also, CUDA graph is in progress. We had some issues with that, so for now we have to pass and force eager to run it with vLLM. Okay, so these are preliminary results on Llama models. We use it as a benchmark. On a small model, smaller model 70B and ISL 4000, there is no overhead on latency. And as we see the cache, we have them like two times more memory for cache, so we can have 43 gigabytes for cache. Without offload, we have only 24. On bigger model, there is no comparison to baseline because the model won't fit into a single GPU. But we wanted to show just what results we could get from the FlexTensor. So on the single GPU, we had around 4,000 tokens per second on FP4 and 1,500 on FP8. When we create the profile, we are calculating some statistics, logs, etc. I forgot to put these numbers here, but we calculated that for the first, for FP4, we would need like 20% more compute time to have no overhead. So we could fully overlap the compute with transfer of tensors. But for the FP8, it is like 2 times more compute would be needed to fully overhead this, to mitigate the overhead. Yeah, and summary. So, as I said, API is quite simple and can be integrated anywhere. Everything is quite automated. Maybe I didn't say this earlier, so there is also possible to manually put offload block in your model if it is needed. So for example, if you have, I don't know, maybe some loop that you want to offload, not like the module, but some part of the code, it is also possible. The interesting thing is shared memory feature. So it allows us to make data parallelism. So we load the model into CPU shared memory, and we can have multiple workers on GPUs, separate GPUs, and all these GPUs will prefetch the weights from the same shared memory. It is not yet integrated with vLLM, but in general, it already works. For future plans, we want to try with training support, Of course, the compile models is a must in quite short time, and also try the same mechanism for KV cache streaming. And that's it from my side. Thank you.